it might not be that complex. It might not be a very simple solution to that problem, right? And it might be a very simple compared to a lot of other complex systems over the years and over billions of years that have been on the planet. For example, an ant colony, very impressive. There might be, other, amazingly complex, colonies of other, types of ants that gone extinct over time, and we left with this simply because they were not optimal enough. So evolution tends to select complex systems for good reason, because they are optimized, right? So if there is complexity in nature, it might be for good reason. And I'm trying to say that evolutionary algorithm and swarm intelligence techniques are a useful application of emergence complexity. So at the bottom line is that, and this is a part of my research philosophy and as well, that it is wise to inspire from natural system. Why? Number one, complex behavior in nature must solve problem efficiently. Number two, and it's quite interesting, a lot of problems in computer science are quite similar to problems in nature, like path planning, scheduling. So we are surrounded by those problems that, already solved by, nature. So it's wise to inspire. And also they are scalable, because we are trying to understand the simple rules that govern those simple units, right? Once we create those, we can then scale it up and create quite interesting patterns without increasing the overall complexity of the system, right? So, and there are some examples, obviously, that I'm going to show you. Finding an optimal path to a food source by ants is unknown in an unknown environment, right? Is similar to finding a global optimum in an unknown search space, right? And they do that by obviously laying pheromone on the ground and some sort of decision making over time. Just to show you a quick demo, and I'll probably finish in a few minutes. So obviously, if you think about each of these individuals, right, they're quite small and stupid all the time. They just use some sort of random walk to go around. But as soon as they spawn a food source, they start to grab a bite and then go back to the nest. There might be other, different paths, and that's exactly what I said. They are trying to search and find an optimal path from their food source to their nest, right? Obviously, this is how we see them in by a naked eye. But if I can, show you a pheromone trail that they use, which shows how amazing that sort of those units now collaborate through external forces to create these sort of complexity, right? So they managed to find a reasonably good path, right? And they are now taking bites, and if I give them enough time, they're gonna, finish those food sources, right? So the reason I'm showing you is that if we can mimic that process in the computer and understand those governing rules, we can then solve problems with them, right? And obviously, traveling salesman problem is a classical problem that you can find in a wide range of areas. The other example, migration in a flock of bird in an unknown environment to minimize energy consumption, because they do that to minimize their energy consumption, is similar to flying in an unknown search space of a problem to minimize the cost function. And we know that there's a lot of algorithm based on these three principles that are able to effectively solve problems. Obviously, this is not purely based on those three governing rules, but I can quickly show you a demo that shows how those simple rules can cause very complex behaviors. So you can see, I think, around 100 artificial particles moving around and bouncing back and forth. They probably don't look like swarm. It's like I don't know, some comets in the space without gravity, right? There are three components, obviously, that create those simple rules that are often called Raynaud rules, right? So we've got cohesion, which obviously maintain integrity between a group of birds. Alignment, they will align their flying path, and separation will avoid collision, right? At the moment, they are zero, but as soon as I engage a little bit, you kind of see we get a little bit of interesting behavior, right? A little bit optimal, right? Because they're trying to, go around and converge to a point, right? If I take this off and we can track their changes over time also, you can see some amazingly and some astonishing behaviors out of them, right? Separations, let's separate them a little bit. See, suddenly they maintain a little bit of distance. Say, I can tick this off to see them live. They still don't look like a flock of birds, probably a bunch of sheep in a herd, right? Grazing the ground, and we are trying to, and moving around, right? But as soon as we engage the third component, see, there's very basic rules, but as soon as we engage the third component, that's where we get these beautiful, flocking behaviors out of these, what's called these small and stupid, really, artificial birds that we have, right? So, and that's what I mean, okay? So if we understand those rules, okay, obviously we can't directly take this and put it in a search space to solve a problem, but obviously we can inspire from this. I hope I'm effectively articulate the point in here. This is my last slide, 2 slides left. So where we are heading, the question is, now that we know the problem is important to formulate, communication with the problem owners are very important as well, and also why we need to, why it's wise to inspire from nature. Let's talk about the future. Let's do a bit of forward thinking. Obviously, we started with heuristics, which are obviously problem specific, and it cannot be reused over and over on different problems. Meta heuristic emerged over time. Those are less problem independent, and in fact, they are black box optimizers mostly, and you can reuse them on a lot of problems. But lately, we've seen a lot of research in the hyperheuristic. It can be as simple as self-tuning, an algorithm that self-tuned itself, or it can be an optimization algorithm that optimizes another optimization algorithm to solve different problems, right? Or you can engage different search behaviors based on the progress of optimization over time, or you can learn even each time and create a memory to learn from experience. So obviously we can see increased automation over time, right? And that's what we are heading, obviously. With the existing technology that we have, with the von Neumann architecture machines that we have, this is the trajectory, but who knows, maybe other technologies like quantum computers will change this, right? If we reach to the point that, anything can be done exhaustively, then we'll talk about a different, the whole new era in the community. Some takeaways from this call before we take some questions. I go back to a famous, saying that, a famous word, everything can be optimized, but the question is why and how. Obviously, the why is quite important. I often see engineers that trying to optimize a part of the system that is absolutely unnecessary. So always think whether you're optimizing is necessary, whether it must be optimized, and how, obviously going back to the problem formulation that we discussed earlier. Some complex natural behaviors can be explained in terms of emergent complexity. Emergent complexity is a great source of inspiration to develop hyperheuristic, meta-heuristic, or hyperheuristic. We can accurately simulate those behaviors to understand them from biological perspective and also solve optimization problems. And that's why often, biologists find our work in this space also important and interesting, because those kind of simulations will help them also to better understand and even scale up and better understand how biological systems work. I think that's all I've got for you today, Dr. Sadullah and everyone else. I'm cautious of time. I think I'm a bit over time, but I will be happy to take some questions.
Thank you very much, Professor, for your interesting and fruitful presentation. I really personally enjoyed it. Thank you very much.
My pleasure.
Yeah, thank you. So is there any question from Professor?
Thank you. Dr. Ali, can you hear me?
Yes,
yeah.
Dr. Anupan, yeah.
Thank you, Dr. Mirjalili. I'm sorry, I just joined late. Maybe the recordings will be available and I'll be benefited. Dr. Ali, I had a very, this curiosity in my mind. You might be the right person to answer it. Because you mentioned many gradient-based methods, and then later on you clarified why we needed meta-heuristics. And I saw some machine learning things as well. My question is, whenever we apply any or develop any machine learning model, then we need optimization as well somewhere in the total modeling. But popularly what it is available, still people are using those gradient based methods itself for optimizing whatever model they have. What you see the scope of these meta heuristics and more precisely nature inspired algorithms in place of those gradient based algorithms? Because
Yes.
I have seen very less papers where these nature inspired have been used in machine learning.
Yeah, and that's a good question, and probably I would say if we focus for now on the training process of a neural network, let's say, or any machine learning, right? It is an optimization process, but why people tend to use a lot of gradient-based algorithm is obviously first because of being able to calculate the derivative of the problem, and second, it's because the problem itself the problem itself can be solved with finding even suboptimal solution, right? And that why? Because often an algorithm like Adam, our tests indicate that it favors flat landscape, right? It's like a heavy ball with a friction that resists to dive into and converge quickly, because the search space of those problems and learning process is of that nature. There's a lot of basing in thousands of dimensions, right? So I would say for the learning process, it will be unwise to use a nature inspired algorithm unless in other stages. Yes, we've done even in my team, we've done a lot of work just to test that and use different algorithms, and we managed to outperform for offline learning. But for online learning and on the fly, is probably better to use those kind of gradient based algorithm, right? And in those applications, the finding suboptimal solution might be also good, because those are the solutions that are not too overtrained, right? They are not overfit the network. Right? But if you're asking in which part of machine learning meta heuristic and nature inspired algorithm can be used, I would say in other stages, like maybe in data cleansing and the feature selection is a challenging problem, can be used. Obviously, it's a binary problem, and we've done a lot of work in that space too. Instead of using PCA, which will reduce the dimension, by finding that relationship, we'll do it as an optimization. Also, if any sort of clustering, obviously, right, for those clustering problems in the area of image processing, I think, which is quite relevant in the deep learning community too. A lot of pre-processing and post-processing can be also formulated as optimization, and a lot of gradient-based algorithm will struggle. So I would see those are the areas that you would want to use those algorithms. Otherwise, if an algorithm is already there and we've got something like Adam that works just fine, why would you bother? That's the question, right? Because it works just fine. I hope that that helps at least to narrow down some of your views around those.
Thank you so much.
No worries.
Thank you so much, Dr. Anupam. Actually, I didn't recognize you. You're a bit changed. Yeah, okay. So are there any questions from Professor Mirjalili?
Is there anything in the chat window? I can't see anything, so no, there's no one.
Professor, I have one question. How to define the meaning of the complexity is mostly depends on the number of design variables or the number of the constraint. Which one is the most important factor to define the complexity of the problem?
I think that's it might be a little bit personal, I think, isn't it? Like, we've got some strength, like I started with single objective, then move on to multi-objective, and then later on constraint because of the nature of problems that I've been dealing with. I think it might be a little bit personal. For me, usually when I have multiple objectives, that's where the complexity, drastically increases, especially when I have so many of them. But I would say maybe the number of those parameters or constant objectives are quite important, right? Because as soon as you have a lot of them, then you feel overwhelmed. You try to simplify the problem. So maybe the number, but for me, it might be objective. But in a lot of real world problems, these are the annoying constraints that makes things a lot difficult, isn't it? Like we had a problem, for example, compressor blade optimization. It's a